Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. We have to actually discuss the idea of directional derivative. Before that, I will refresh your memory about the idea of a field. So what is a field? Now, you know, many physical quantities have different values at different points in space. For example, the temperature in a room temperature in a room temperature in a room is a field. It has different values at different points in space. Similarly, the electric field around a point charge is a field. The electric field around a point charge. As you know, if we have some point charge, positive, it can be negative as well. At every point surrounding it, there is a field. For example, at point P, there exists electric field at point P that has certain magnitude and certain direction. Direction is radially outward. So there is a vector electric field at every point surrounding this charge. There can be another examples. Air pressure inside a room is also a field. Now, in all these examples, there's a particular region of space which is of interest for the problem at hand. At every point of this region, some physical quantity has a value, right? For example, in case of temperature, if you are interested in the field within a room, then within that space, temperature is a physical quantity which has value at every point. Similarly, if you are interested in electric field surrounding some charge, the space surrounding the charge has electric field at every point. So when we say the term field, this term field is used to mean both the region and the value of the physical quantity in the region, right? Both the region and the value of the physical quantity in the region combined means field, right? We can have a scalar field, we can have a vector field. For example, temperature is a scalar field because this temperature is a scalar quantity. Vector field, electric field is the example of vector field. Similarly, gravitational field is the example of a vector field, right? So, because gravitational field and electric field are vector quantities, right? So, I hope this idea of field is now clear to you. So, let us move forward. Now, we will discuss the idea of directional derivative. And this directional derivative embodies the idea of another idea called gradient. So let us explore both of these. So suppose we have a scalar field. Suppose we have some scalar field phi. I write it phi of x, y, and z. That means if this is my space, at every point of it, this phi has a value. So I have a field in space represented by phi, and I'm assuming it is a scalar field. So it is scalar quantity. It can be temperature field, it can be some other pressure field, right? We're talking in general terms, right? Now, what is a directional derivative? We want to find d phi by ds. D phi by ds is the directional derivative of this scalar field phi. What is the meaning of d phi by ds? It is actually the rate of change of phi with distance at a given point. That point can be, for example, x naught, y naught, z naught, and in a given direction, right? So when we find the rate of change of phi with distance at a given point and in a given direction, we say we have found the directional derivative of this scalar field phi. I hope it's clear to you. That means we're first fixing a point. At that point, we are moving in space, finding rate of change of phi with distance in a specific direction. Suppose, now how we find it? Suppose u cap is a unit vector in certain direction, u is a unit vector in certain direction. Now we want to find directional derivative at some general point in that direction. So how we write it? Let me use another color. This d phi by ds, directional derivative of phi, is del phi dot u cap. That means to find the directional derivative of phi in the direction of unit vector, what you have to do, you have to find this dot product. What is this del phi? This read as del phi, where del phi is called gradient of phi. Gradient of phi, it is written as grad phi. And mathematically it is this: I cap do phi by do x plus j cap dou phi by dou y plus k cap dou phi by dou z. So you can see this gradient of phi or del phi, it is read as del phi, has three components. Is a vector like thing. It has three components. Its x component is partial derivative of phi with x, its y component is partial derivative of phi with y, and its z component is partial derivative of phi with z. So if I am given some function, some scalar field phi, and I am asked to find uh, uh, directional derivative of that particular field in certain direction at certain point, then what I do first, I have to figure out these partial derivatives and construct my del phi. Once I find this del phi, then I fix the point, I put the values of x, y, z, and that will specify the gradient at that particular point. Then I dot it with the unit vector in that direction and complete the process. This is the recipe for calculating the directional derivative of a given scalar field. Now, it has this gradient of a function has geometrical and physical meaning. What is that? Geometrical and physical meaning. Suppose this is a contour. What is a contour? It's a level surface of phi. That means in space, at different points, you have values of phi. Now, if you join all values of phi having same value, that means if you join all points having same value of phi, you construct a surface that is called contour of phi or level surface of phi. For that, I am showing that surface. So that means over that surface, phi is constant, everywhere phi is same. Now, suppose there is certain direction, and in that direction, we are constructing a unit vector. Let there be unit vector in some particular direction. And suppose this is my del phi vector, gradient of phi vector here, right? And this is angle between this vector gradient of phi and this unit vector u cap. Now see, dou phi by dou s is the dot product of del phi with the unit vector. That means if theta is the angle between del phi and the unit vector, you can use the ordinary rules of dot product. That means it is just del phi, magnitude of del phi vector into cosine of theta, because the magnitude of unit vector is 1. Simple dot product. A dot B is magnitude of A, magnitude of B into cosine of the angle between the vectors. So similarly, dot product of del phi with unit vector is magnitude of del phi times magnitude of unit vector, which is 1, times the cosine of this angle theta. So what is del phi cos theta? Del phi cos theta is just the projection of this del phi on this unit vector. That means this length, I will use some other color. That means this length is what? This is del phi cos theta. that is equal to d phi by ds in this direction, right? It is d phi by ds in the direction of u cap. So you can see geometrically when I am finding the directional derivative of phi in the direction of unit vector u cap, I am actually finding the projection of this gradient of phi along the direction of u cap, right? Now, the largest value of d phi by dx is, what is its largest value? Because if you change the theta, its value is going to change. Its maximum value is when theta is 0, and that is just del phi. Because cos 0 is 1 when theta is 0 degree. When theta is 0 degree, in that direction, this maximum value of this gradient, directional derivative is equal to what? Magnitude of the gradient. So that means the largest value of the directional derivative is equal to the magnitude of gradient of phi, and this is in the direction of theta 0. That means if I move in the direction of the gradient itself, if my unit vector is in the direction of the gradient, I will have the maximum value of directional derivative in that particular direction. Now, if I move in the opposite direction of del phi, that means when theta is 180 degrees, cos 180 is minus 1, then my directional derivative will be minus times the magnitude of this gradient of phi. That means if you move in the direction of gradient of phi, directional derivative will have maximum value, and if you move in a direction opposite to the direction of gradient of phi, directional derivative have minimum value. So I can say that the largest rate of increase of phi where distance occurs along del phi, and the largest rate of decrease of phi occurs in a direction opposite to that of the gradient of phi. This is how we interpret it physically and geometrically. We will go through a simple example to understand it. Let us move to that example. This example goes like this. It says find the directional derivative of phi. Let me write it downstairs. Phi equal x square y plus xz at 1 to minus 1 in the direction a equal to 2i minus 2j plus k. Let me check it. Find the directional derivative of phi equal to x square y plus xz at 1 to minus 1 in the direction A equal 2I cap minus 2J cap plus K cap. Understand the question first. See, I am given this scalar field phi. I'm asked to find its directional derivative at a particular point, which is 1, 2, minus 1 in a particular direction. That is in the direction of vector A. So let us move to the recipe. What is the recipe? Recipe is this. So first I have to find the unit vector in the direction of vector A. Then I have to dot that with del phi, for which I have to find the partial derivatives of phi. And then I have to do the dot product. So let us do solution. Let me use another color, this one. Here, u cap is a unit vector obtained how? How you obtain unit vector in the direction of a particular vector? You divide that vector by the magnitude of that particular vector. So u cap is a unit vector obtained by dividing vector A by the magnitude of A. So what is u cap? 1/3 times 2I minus 2J plus K cap. This is my unit vector. Let me encircle it. This is unit vector in the direction of A. Unit vector in the direction of A vector. See what I have done. First, you have to find the magnitude of A. What is the magnitude of A? Magnitude of A is square root of x component square, which is 2 square plus minus 2 square is y component plus z component is 1. This whole thing in the root. So it is 2 square is 4 plus minus 2 square is 4 plus 1 square is 1. So it is under root 9, which is 3. So this 3 is magnitude of A. So what you do to find the unit vector in the direction of A, you divide A, which is 2I cap minus 2J cap plus K cap with the magnitude of A, which is 3 units. So we have obtained unit vector in the direction of vector A. Now, let me use another page. Now I find the gradient of phi, which is what? Which is I cap dou phi by dou x. Let me write it neatly. Dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. So let us find these partial derivatives. I will write them directly. It will be 2xy plus z I cap plus j cap x square plus x k cap. 2xy plus z I cap plus x square j cap plus x k cap. That means I am saying dou phi by dou x is 2xy plus z. Dou phi by dou y is x square and dou phi by dou z is x. Chuck this at home. Chuck it at home. Dou phi by dou x is 2xy plus z. Dou phi by dou y is x square. And dou phi by dou z is x. Now I have to specify the point. This is general dou phi at some general point x, y, z. Now, del phi at 1, 2, minus 1, which is the point in question, 1, 2, minus 1. That means x is 1, y is 2, z is minus 1. You have to put for x 1, put for y 2, and put for z minus 1. When you do this, you will get 3i cap plus j cap plus k cap. That means del phi at this given point 1, 2, minus 1 is 3i cap plus j cap plus k cap. Now the final step, we have to find the directional derivative in the direction of vector A. So directional derivative dou phi by dou s at this particular point 1, 2, minus 1 is just the dot product of del phi with u cap. Let us do the dot product. This is my del phi. And where is my unit vector? This is my unit vector. How we do the dot product in component notation? A dot B, you have to just multiply the corresponding components and add them. Ax bx plus ay by plus az bz. Right? The same thing is here. X component u cap is 2 by 3 and x component of this is del phi at this particular point is 3. You have to multiply them. You will get this answer 2 minus 2 by 3 plus 1 by 3, which is 5 by 3. So this is my answer. Check it at home. You have to multiply 3 with 2 by 3, that is just 2. Then multiply 1 with minus 2 by 3, that is just minus 2 by 3. Then 1 with 1 by 3, which is 1 by 3. So it is 2 minus 2 by 3 plus 1 by 3, which is 5 by 3. Right? It's 5 by 3. That's my answer. 5 by 3 is the value of the directional derivative of this particular scalar field at this particular point in the direction of the vector A. I hope you got the idea. So this is all for today. Go through all the video lectures and all examples and all homeworks. When I say check it at home, do a check at home. And don't forget to like, share, and subscribe my channel. You can give comment in the comment box, good or bad, no issue. Thank you. God bless you. Assalamu alaikum.